Percent dissociation. When we deal with percent dissociation, we're dealing with the amount of a weak acid that has dissociated when equilibrium has been established. So to calculate the percent dissociation, it's really the same thing as what we've been doing to prove that X is insignificant in our equilibrium problems. We're going to take the amount of the acid that dissociates, that's our X value when we solve, divide it by the initial concentration we begin with, and multiply it by 100. So if we know that a 1.00 molar solution of hydrofluoric acid has an equilibrium concentration of hydrogen of 2.7 times 10 to the minus 2 molar, what's the percent dissociation? So what we'll do is we'll take the amount of acid that dissociated, which is equal to the hydrogen ion concentration. So 2.7 times 10 to the minus 2. We'll divide it by the concentration of our original acid, which is 1.00, and multiply it by 100 to make it a percent. So we're going to get 2.7% for our percent dissociation. 2.7% of that acid actually dissociates into hydrogen ions and fluoride ions. So let's look at a problem that incorporates this percent dissociation. It says lactic acid is a waste product that accumulates in muscle tissues during exertion, leading to pain and a feeling of fatigue. If a 0.100 molar aqueous solution of lactic acid is 3.7% dissociated, calculate the value of K for this acid. So this time we're going to kind of work the problem backwards. We don't have K and we're trying to figure out what the hydrogen ion concentration and the pH is. This time we're going to be able to figure out what the hydrogen ion concentration is and work backwards to calculate K. So we'll start with our equations. Again, we've got water and lactic acid. We're only going to deal with lactic acid for this problem. So HC3H5O3 is going to dissociate into hydrogen ions and lactate ions. So C3H5O3 minus. We'll fill in our ice chart. The initial concentration of our lactic acid is 0.100 molar. And it doesn't mention anything in the problem about having any hydrogen ion or lactate ion in the solution initially, so we'll put down zeros. It's a weak acid, some of it dissociates, so we'll put in 0.100 minus X, X, and X, and we'll write our Ka expression. So Ka equals our hydrogen ion concentration times our lactate ion concentration over our lactic acid concentration. We don't know Ka this time, so we're going to have to work the problem backwards. And we're going to do that by looking at the percent dissociation. It tells us in the problem that it's 3.7% dissociated. So 3.7% equals the amount of acid that dissociated over the initial concentration times 100. So we've got 3.7% equals X over 0.10 times 100. So we'll divide both sides by 100, multiply both sides by 0.10, and we get X equals 3.7 times 10 to the minus 3. And that's our concentration of hydrogen ion And it's the concentration of our lactate ion once equilibrium is established. Our percent dissociation is less than 5%, so our concentration of our lactic acid at equilibrium is going to be 0.100. Now we can plug those numbers in here. We've got 3.7 times 10 to the minus 3 for our hydrogen ion. We've got 3.7 times 10 to the minus 3 for our lactate ion, so I'll just write squared. And we'll divide it by that 0.100 concentration for our lactic acid. And that's going to give us a Ka value of 1.4 times 10 to the minus 4. So this time we're just working the problem backwards. Instead of being given Ka and we're calculating the ion concentration, this time we can figure out the ion concentration and then calculate Ka.